Okay, welcome Brittany and Mark and Kate and David and Mike and Calvin and Savannah. Thanks for showing up at the week 3 webinar. What we're going to be doing today is chapter 4, which is a chapter on discrete distributions, and chapter 5, which is a chapter on continuous distributions. So that's kind of the plan. It's actually not one of the heavier weeks, but again, this is also a week that you should be starting to work on your project in a big way. So it's heavy in that way. Even though we have 2 chapters, that sounds like a lot. The combined chapter 4 and 5, most people find is much easier than just chapter 3 by itself, because that was a hard chapter. And you probably agree with me on that. So are there any questions about anything before we get started? Any questions? Okay, let me get started. Is your guys' audio sound muffled? Uh-oh. Are you having trouble hearing me? Not sure what I can do about that. It's the same as I always use, nothing's different. Okay, so some are muffled, some are little, and some are not at all. That one's really hard for me to figure out. But let me talk about what we're doing. And what I thought I would do is I'm going to show you what I've been working on this weekend, okay, over the past weekend. Of course, half my time was spent skiing because it was absolutely amazing powder weekend. But the other half of the time, I actually coded. And I made a game. And I thought we'd play the game. So let me show you the game I created. And it's in the textbook now. That's what I like about this version of the textbook, is that I can go in and put stuff in. So there's a game now. So let me show you what it looks like. And let me go to share. And here and here. There. Okay, so this is book 4.3. And the good news is I have the ability to put whatever I want in it. It's an open book, and that's one of the good things about free and open, is that I can also put stuff in. So I coded a game, and let me scroll down. I'm going to show you, and I recommend you playing this too. See how y'all do. So it's be the player or the casino expected value game. And here is what it says. You'll be given the rules to a randomly selected hypothetical casino game. Then compute the expected value, and based on the result, choose to be either the casino or the player. Then 10,000 games will be played, and you'll either win or lose that amount of money, in theory. We're not going to give you any money if you win, but you can imagine it. So I'm going to click Next Game, and we're going to look at it. Okay, so this game involves a wheel. And the wheel has 86 colored slots of colors blue, orange, green, and red. 6 of them are blue, 7 are orange, 3 are green, the rest are red. Okay, if the spinner lands on a blue, the player wins $12. If the spinner lands on an orange, then the player wins $14. If the spinner lands on a green, then the player wins $15. If the spinner lands on red, then the player loses $6. So the question is, should you be the casino or the player? Okay, and any guesses?
Always be the casino.
Any guesses? What do you think? Better to be the casino or the player?
Casino.
Okay. All right. Mike says player, Kate says casino. So the idea is you really can't tell until you actually do the calculations. And that's kind of half of what chapter 4 is. So I want to mention a couple things. The first is that this is what's called a discrete variable. Okay, it's quantitative because it's in terms of what you're going to have, you're either going to end up with 12, 14, 15, or -6. Let me actually write that down. 12, 14, 15, or -6. Any questions on that? Okay, you can list all of the different possibilities. And when you can list all the different possibilities and their numbers, we call that a discrete variable. Okay? When you have a discrete variable, usually the first thing you want to do is create what's called a probability distribution table. And a probability distribution table means that you write down the values and the probabilities. So notice that we had 86 color slots. Okay, 6 are blue. Okay, 6 make you win $12. Okay, and you also have 7 are orange. We have 3 are green. And the rest of these 86 are going to be red. So I'm going to unshare for a bit and reshare. I'm going to go into Paint so I can start drawing stuff. So the first thing I'm going to do is I'm going to draw what's called a probability distribution table. And I'm going to do that. It's going to look like a T-table. I'm sure you've seen T-tables before. And the values, the left will always be X, and the right will be P of X. P stands for probability. Any questions so far? Then what I'm going to do is I'm going to write down all the possible values that could happen for X. So for example, one of them was 12, you win $12. Another was 14. Another was 15. And then another was losing 6, that's a -6. Any questions on that? Then I'm going to write down the respective probabilities of these values happening. So let me go ahead and put those numbers in. Right about there. So notice that there were 86 different numbers. 6 of them ended up winning $12. So it's going to be 6 divided by 86. Remember, probability is always a fraction. And then for the $14, that was 7 of them made you win 14. 7 over 86. And then to win $15, there were 3. How do you find out the probability of losing $6? What do y'all think? Yeah, what we do is we subtract from 1, right? Because remember, all the probabilities together have to add to 1. So I'm just going to write it as a fraction, 86 over 86, minus 6 over 86, minus 7 over 86, minus 3 over 86. Or I can say add up 6, 7, and 3, and you get 16. 86 minus 16 is 70. So you get 70 over 86. And that's going to be the probability of losing that $6. Any questions so far? Okay, now that we have our probability table, what I'm going to do is I'm going to find what's called the expected value, which is like the mean and the standard deviation. How I got 6 over 86. Oh, that was given in the problem. It said, let me go back to the problem and I'll show you. So we see that 6 of them are blue, and there are 86 colored slots. So that's 6 over 86 for the blue ones, and the blue ones, remember, that was winning a 12. Mark, does that make sense? Yeah, so that just came from the numbers. It's not that deep, I promise. The hard part about this is going to be recognizing that this is what we need to do. Like realizing this chapter when you have it on the final or the midterm. Okay, so now what I'm going to do is I'm going to go to my calculator. You're used to that. So what I'm going to do is I'm going to go to Stat. Then I'm going to go to Edit. In L1, if you have stuff in L1 and L2, you gotta clear them out. I don't right now, so I just don't have to worry about it. I have 12, 14, 15, and negative 6. 12. Oh, shoot. Let's try again. 12, 14, 15, and negative 6. Notice it's negative 6, not subtract 6. And they're actually different on this calculator. Then I'm going to go to L2, and I'm going to put the probabilities. And that was, if you remember, 6 divided by 86. And then 7 over 86. And then 3 over 86. And then 70 over 86. Any questions so far? All right, so now what I'm going to do is I'm going to go back to Stat, and I'm going to go to Calc, 1var Stats. If you have the older kind of calculator, it'll look different. And then you'll watch the video from the chapter video, and that's the older kind. My list is L1, so that's good. The freak list now is going to be L2, so I can go second, 2. That gives me L2. Then I'm going to get on calculate and hit enter. All right, any questions so far? Okay, so now what we have is x bar is equal to negative 2.38. I'm just going to keep it as 2 decimal places for now. And we have the standard deviation, sigma, equals 7.58. So x bar is called the expected value. You have to put 12 L2 for the freak list. Yes. Yes, you have to put, because you have to tell the calculator, grab the numbers that you put in for the probabilities. Does that make sense, Pidja? Otherwise, it won't know that those probabilities even exist. So that's what you're telling the calculator. So it's the first time really we used L2 in a big way. All right, so now I'm going to reshare. And let's go back. All right, so first write down expected value is equal to negative 2.38. So what do you think? Do you want to be the player or the casino? Yeah, it's negative. Who wants to lose money? So what we could say, and let me interpret the expected value now. This is very important. What we can say is that if many such games are played, then it is very likely that the average amount, and I'm going to write lost, and then I'll get rid of the negative sign. If you have lost, then it's positive. Per game will be close to $2.38. How did I get the expected again? So that was X bar on the calculator. Yeah. So that was the very first number. It's the mean. So the expected value is the mean, but it's the mean for a probability distribution table. So we call it expected value. So I want to note something that's very important. I want to underline some keywords. Oh, what just happened? Oh, I know what happened. I lost it. Well, let me type it in one more time because it's too important. I don't want to lose it. I'll type fast. So if many games are played, then it is very likely that the average costs per game will be close to 238, 2.38, $2.38. I think I didn't click off, and that's why it lost it. So I want to underline some very important things to note. Many, very likely, average, and close to. Okay, those words are necessary. Okay, you miss any of those on a test, I take off points. Got it? Okay, so we're talking about lots of games, talking about averages. We don't know it's going to happen, but it's likely to happen. And it's not going to be exactly the expected value, but it's likely to be very close to the expected value. Any questions on this idea? All right, let me go back to the game because we got to play, right? So by the way, we're going to be the casino because that's a smarter thing to do, right? So let's reshare. So I'm going to choose to be the casino. Should we play the game? Okay. So if you're the casino, notice the expected value is positive 2.3837. And my casino just won $22,000. Okay, if you were the player, guess what? You'd lose. Okay, doesn't mean you're going to win every time, but you're likely to win. And notice we're playing 10,000 games. That's many. Any questions on this idea? Okay, by the way, I recommend you go into the book and playing this. If you hit next game, you'll get a different game, by the way. Okay, that's what I get. I did that this weekend. I programmed a bunch of games in, and then all the numbers are randomized too. So it'll be different, but same idea each time. Note, by the way, the standard deviation was 7.58, which is pretty high, $7.58. So if you just play a game or two, you may end up winning as a player. But many games, that's different. It's very likely to win, very unlikely to win. If the standard deviation is low, then then even with one game, you're likely to be very close to the expected value. Any questions on this idea? The casino is positive. If I'm the player, notice it's negative. Does that make sense, Pooja? So it's negative for the player, and of course, if the player loses, the casino wins. Yeah, and that's just, I know you don't live in Tahoe, but we're a casino town, so I figure I'd throw some casino stuff in. And I've actually consulted for the casinos on this stuff and helped them make sure that anyone who comes in loses.
What haven't you done?
So it's all my fault. Okay, so That's expected value. Any questions on the idea of expected value? Okay. Next, I'm going to talk about something kind of depressing. Sorry about that. But I'd say I started doing this about 10 years ago. And what I looked at was I looked at the statistics of global warming. Okay, in those days they called it global warming, not climate change. But in particular, we're looking at global warming. And the question is, let me show you the data, by the way, for the last 10 years. So here's the data from the last 10 years, or the top warmest years. Notice, do you notice something? They started, by the way, they started measuring in 1880. This should say 2019. This is, whoever wrote this made a little mistake there because they actually did put this in for 2019. And by the way, last year was the second warmest year in history. Okay, so here's the data. And you might notice that in the last 10 years, that's 2010 through 2019, you'll notice that 8 of the warmest years, or 8 of the last 10 years are in the top 10 warmest years. Does that make sense? Just by looking at this data here? Because we got 2016, 19, 15, 17, 18, 14, 2010, 2013, 2005, and 2009 are not in the last 10 years. Is that clear? All right, so here's the question I have now that we've seen this. Okay, sorry if it's depressing, but you know, it's reality. So the question I have is the following, and let me put paint up again so I can start typing. I'm going to erase this now. So the question is the following. If the temperatures are due to random chance, okay, so that means that, you know, we haven't changed anything recently, has nothing to do with us, and there are some politicians that'll tell you that. I won't, by the way, because we're going to take a look. So if it has nothing to do with us and it's just every year is a random year, what is the probability that at least 8 of the of 10 selected years, and actually write randomly, will be in the top 10 warmest years on record? Any questions about the question? Any questions? Okay, I want to mention some assumptions that aren't quite right, but we're going to make them anyway. We're going to assume that each year we're grabbing is independent of every other year. Okay, it turns out scientifically that's not perfect, but they've also looked at the non-human things in the last 10 years, and they found out that there's nothing going on like solar flares in the sun or anything like that. So that's not too big a deal. And we're going to assume, even though it's not quite true, is that we're doing this with replacement, which isn't quite true, but it turns out the probability is not that much different anyway. And in fact, it's going to be a lot less if you do it without replacement. All right, so I want to note something. The first is if you look at any individual year, what kind of question is this? Is it qualitative, quantitative? What is this? So if you look at any specific year that you're testing, what kind of question? Yeah, in particular, it's qualitative, and even more so, it's qualitative yes, no. Does that make sense? Because either yes, it's in the top 10 warmest years, or no, it's not in the top 10 warmest years. Is that clear? So if you have, let me write down all the different things. If you have a group of yes, no, independent questions where each has the same probability of a yes answer, then we call it a binomial experiment. Any questions on this? So we're in the case of a binomial experiment with those assumptions because it's a bunch of yes-no questions, right? Each year we're asking and it's yes or no, and each year has the same chance of having being in the top 10 warmest years, given that people have nothing to do with climate. So the question is, given that people have nothing to do with climate, what is this probability? So I want to mention, and for most of the calculators you guys have, it can't handle at least 8. So what I'm going to do, and I strongly recommend you do this on every one of these kind of problems, is just write down numbers near 8. So how about 5, 6, 7, 8, 9, 10. Then what you should do is say, what is at least 8? Where does at least 8 start? What's the smallest number that's at least 8? Not 7, not 1, 8. So here's the way if you're having trouble understanding this, here's the way I like to think about it. You must be at least 21 to go to the bar. Do y'all agree? Okay, can a 4-year-old go to the bar? No. Can a 21-year-old go to the bar? Yes. 21 and up can go to the bar, right? That's the at least, because hopefully you're all familiar with that sentence, right? You must be at least 21 to go to the bar. So what I'm going to do is I'm going to circle all the numbers I'm interested in, the at least 8, which are 8, 9, and 10. The calculator cannot handle the right-hand side, so we have to use the rule of complements. So what I'm going to write is the probability that x is at least 8, which is less than or equal to 8, greater than or equal to 8, is equal to 1 minus the probability that x is less than or equal to what number? And the key is, what's the biggest number that's not circled? 10 is circled. 6. Well, no. 7. There you go. Yeah, 7 is the biggest number not circled. So the complement of greater than or equal to 8 is less than or equal to 7. Any questions on that? Okay, a lot of people have a lot of trouble with this. That's why I wanted to spend a bit of time on it. All right. Now, what we're going to do is we are going to go to our calculator. Okay, and let me write some things down. So what we say is that our sample size, n, maybe I'll even type this in, n is equal to 10. The probability of being in the top 10 from 1880 to 2019 is going to be 10, because there's 10 years in the top 10, over 140, because there's 140 years between 1880 and 2019. We could say X is going to be equal to 7, because that's what's in the above in terms of what we turned it into. Let me actually write that down because I'm about to lose the screen. So n equals 10. We have p equals 10 over 140, and x equals 7, and it's a 1 minus. So now we get our calculator. And let's clear what we had. So now what I'm going to do, and this is a new button for us, we're going to go to second distribution. This is VARS button after hitting second. Then you're going to scroll down a bunch until we get to binom CDF. CDF means less than or equal to, PDF means equal. So it's a binom CDF. I'm going to hit enter. This is the newer calculator. The older calculator, you'd put what I'm putting in with commas in between and a parenthesis at the end. But the newer calculators, the number of trials was 10. P was 10 over 140. The X value was 7. And I enter. So if you have the old calculator, it's going to look like this. 140 years between 1880 and now. That's how long they've been recording the temperature. And Kate, you wanted me to repeat the definition of binomial? So that was every question is yes, no. We have many, we're going to ask many. Each one has the same chance of saying yes. And they're independent of each other. Is that clear, Kate? Okay. So then I just hit enter. Okay, but remember I want 1 minus, so I'm going to go 1 minus. I'm going to go second answer. That's how you can pull up what just happened with binomial. So is the probability 2.67? What do you think? Is our probability 2.67? Yeah, definitely not, because that E negative 8, that's sign of indentation. What it really is 0.000000267. So what do you think? Pretty likely? Definitely not. Notice, by the way, this is, in terms of how you read this, is tens, hundreds, thousands, 10,000, 100,000, million, 10 million, 100 million. So we're actually about 2 or 3, 2.6 out of 100 million possibilities. So it turns out, actually, the probability of this happening randomly is actually less than the probability of that. Remember that lottery ticket from last week? The lottery ticket from last week actually had a higher probability of winning than picking 10 random years and having at least 8 of them being in the top 10. Okay, and by the way, do you think I won the lottery?
No.
No, of course not. Okay, not only did I lose, but it was an ugly loss, worse than I usually lose. Not one number matched in all of the numbers. Okay, so anyway, winning the lottery is more likely than this to just happen randomly. So what do you think? Do you think it happened randomly? Right? Do you think that's the explanation? I know that was not the explanation. We did it. That has to do with all the fossil fuel we're using and all the other stuff that lets out methane and carbon dioxide. And it's very clear scientifically what's happening. And unfortunately, a lot of people listen to politicians instead of scientists and statisticians. But hopefully you listen to the statisticians because we know what we're doing. Okay. And the scientists too, to know that, what the causes are. Any questions at all on this example? Okay, so just note, I can't do every type of example, but there aren't that many different things. Other things that could happen, let me reshare and I'll tell you some other things that could happen that I could have asked that I didn't. I could have said, what's the probability that exactly 8 of the years were due to that? Do you have to write your answer in decimal form? It's a good idea because it shows what's going on a lot better. Okay, but you definitely can't write 1.67. That's not okay, or 2.67, whatever the number was. Okay, you can't do that. You have to at least do scientific. E is not proper form, by the way. So that's never allowed. Whether you're doing it on the assignments on the computer or on the test, you should never have an E because that's not standard notation. It's 10 to that power is what it is. Okay, but better is decimal form. Okay, other things that you could ask is probability of exactly 8. What would you do to be exactly 8? I mentioned it. Yeah, basically the same thing. There wouldn't be any 1 minus, but you'd have the same binom, but it'd be PDF, and then you'd have 10 over 148. Okay, so if it was exactly, it could be, say, less than 8. And then you do binom PDF with a 7. It could be less than or equal to 8. You do binom PDF with an 8. So there's different combinations like that you could be asked, and you'll practice those. And if you ever have troubles, you can always post on the Q&A forum. But I have a whole other chapter to do, and I want to make sure we get to it. So any questions on chapter 4? Any questions? Okay, so let's move on to chapter 5. All right, so the first thing is we talked about a discrete probability distribution or discrete variable. And a discrete variable means that you can list all the possibilities. Okay. Does it have to be whole numbers, a discrete variable? What do you think? Like here we had, 8, 9, 10, the listed that I gave. Does it have to be whole numbers? What do y'all think? Yeah, it turns out it doesn't. Let me give you an example. Let's see if you can put this answer in. How many siblings, and by the way, including yourself, are in your family? Type in the box. And I'm going to type it in also. I'm always the only one that does this. So once in a while I'll see it, but is it letting me? There we go. All right. Did you see mine? I'm the only weird person, I guess, okay? No, this is real. You're ha-haing, but it's actually real. There's Laura, okay? You don't have to know Laura, but she's my half-sister. And that could happen, right? Trust me, it could happen. I have a half-sister, okay? And there's 4 that are my full siblings, as they say. So I have 4.5 siblings, including me. Any questions on that? Okay, so you can have halves, but you can't say have 3.1724 siblings. That doesn't make any sense at all. So it's okay to have a few possible fractions in there, but what you can't have is every single possible fraction that could ever happen. That wouldn't be discrete. If you have every possible fraction in between, so all the different numbers and all the real numbers, then we call it continuous. So let me write that down. So the continuous variable is not countable. You can't just list them. Okay, can you draw, if it's a continuous distribution or continuous variable, can we draw a table like I did for the discrete, where we had the x and p of x? What do you think? Right, the answer is no. If you can't list them, you can't put them in a table. So let me tell you what you do instead. If you can't put them in a table, what we do is we draw a graph. And the bad news is, most of the time, but not always, the graph, the math behind the graph, the equation of the graph will be too hard for you to understand. So this is the most important example. And we've seen this one. What do we call that one? Yeah, that was normal. Okay, that's the most important, and we'll get that next week. So we're not doing that one, but I wanted to show you how things look. So if you want probabilities, so let's say we have a normal distribution, and let's say this mean is, say, 4. And let's suppose this is a 3. And let's suppose this is a 5. Then if we want, say, the probability that we're between 3 and 5, here's what we do. So let me write that first. Probability that 3 is less than x is less than 5 is going to look just like the following. So now I'm going to go to my brush, do it in red. I'm going to take 3. I'm going to take 5. I'm going to draw a little vertical line segment. Then I'm going to shade in the area under the curve between 3 and 5. So let's write that down. Is the area between 3 and 5 under the curve and above the x-axis. Any questions on the idea of probability when you have a continuous distribution? Okay, now, as I mentioned, if you try to do this by hand, you would cry. Trust me, you can't. But there are some examples, one very special example, that you can do by hand. What is the one example, okay, there's probably 2, but one main example, that you first learned in terms of how to find area? What shape? Yeah, square, a little more general, not much more general, but a little more general. Any idea? Yeah, rectangle. So if the probability distribution is a rectangle, so now let me draw it again. By the way, I'm using a mouse. It's not easy to draw. That's supposed to be a straight line. That's a rectangle. Let me write down rectangle because it doesn't look perfect. So there's a rectangle. Then we have a word for it. This is called a uniform distribution. Right? And if you think about it, why do military people, Mark, have to wear a uniform? Yeah, what's the reason for wearing a uniform?
Individuality.
Any thoughts? Should I tell you? See, so you all look the same. Yeah, yeah, everyone has to be unified in the same. So notice when you have a uniform distribution, the y value is always the same. Does that make sense? So when you have a uniform distribution, the y value is the same. So for example, if we looked at let's put some numbers in here. Oops, I need to first click. There we go. Let's suppose this was 3 right here. And let's suppose this one was 11. Then if I found the area between, say, 4 and 6, that would be the same as the area between, say, 8 and 10. Do you agree? As long as my x width is the same, I always get the same answer for the area, which is probability. So the probability of being between two equally width values within the range of the uniform distribution is always the same. Any questions on this? All right, so we're going to spend the rest of the time on the uniform distribution, and I'm going to get rid of what I got because I got to put some questions in now. So now let's put some questions in. It takes a moment to get there. And I got hiccups, which means I need water. Okay, so here's the question. Okay, suppose that the time that students spend in the Math Center is uniformly distributed between 10 and 120 minutes. And then it says, be sure to show your uniform distribution charts. Okay, and then the first part is if a randomly selected math lab user is observed, find the probability the student will spend between 30 and 70 minutes in the lab. Any questions on the question before I get into it? Okay, the first thing I'm going to do is draw the picture. So let me show you how the picture looks. It's uniform. Okay, and I want you to know if you don't see the word uniform, do not draw a rectangle. Got it? And if you do see the word uniform, then it's a rectangle. because next week we're going to have normal, and those aren't rectangles. Okay, we know that it's uniformly distributed between 10 and 120. So let's go and type in 10 and 120. All right, how do I find out how high this rectangle is? How do I find out the height? Any thoughts? Yep, base times height. But what is the area? What is the area of this rectangle?
1.
Yeah, it has to be 1, because there's a 100% chance that you're between 10 and 120. So what we can say is that area equals the base times the height, and that is equal to 120 minus 10 times the height, and that is equal to 1. Any questions on what I just did? All right, now I'm going to do everybody's favorite thing in the world to do, which is algebra. Okay, there's a little algebra in this class, not too much, but a little bit. And that is, we need to solve for h. Okay, so how do you solve for h? Yeah, what I'm going to do is I'm going to say 120 minus 10 is 110, and then I'm going to divide both sides by 110. So I could say h is equal to 1 over 110. Is that clear? Any questions on what I just did there? All right, now let's answer the first question. We want to find the probability the student will spend between 30 and 70 minutes. So now what I'm going to do is let's mark those 30 and 70. And draw the picture. So it goes from 30 to 70, and I want to find that area. How do I find the area? Notice it's a rectangle. Any thoughts? I'll put it up on the top. So it's a rectangle. Area equals the base times the height. Right? What is the base of this blue rectangle that goes from 30 to 70? What is the base?
40.
Yeah, 40. I'm going to actually do the work. It's 70 minus 30 is how you found the base. And the height was 1 over 110. And if you work that out, that's 40 over 110, or 4/11. And I've now answered the first part. Any questions so far? All right, now let's look at the next part. The next is find the first quartile. Who remembers what first quartile means? Yeah, it means that 25% is at or below that value. So let me remind you, I'm just redrawing the picture because we need to do that. So again, we went from 10 to 120. It's the same rectangle. Okay, so I want to redraw the picture. Notice that 25% is not an x-axis value. It's an area because that's the probability. This is going backwards. So what I'm going to do now is I'm going to draw the picture. And we don't know this value somewhere around here. So let's call it Q1. Sound good? For first quartile. Then I'm going to draw the picture of the rectangle. And I know that from Q1 to 10, right, like that, has area 0.25. Any questions on that? Okay, so now it's time to set up the formula, just like I did when I tried to find out the height. Now I'm trying to find out Q1. Okay, it's going to be a little algebra. So what I'm going to do now is do area is base times height, just like before. And what that means is the area is 0.25. The base, we don't know exactly what the base is, but it's Q1 minus 10. The height was 1 over 110. Any questions on that? We want to find Q1. How do we find Q1? What's the first step? And again, algebra. That's a hint. Q1 minus 10. What are we doing? What algebra are we doing here? We could divide, but it's easier to multiply actually. Because we have a divided by 110, if you multiply both sides by 110, then what you end up with is getting rid of that 1 over 110. So let me kind of demonstrate that. So I'm going to multiply both sides by 110. And what I get is 0.25 times 110 is equal to Q1 minus 10. Any questions on it? All right, I want Q1 by itself. What's the last step? Yep, add 10 to both sides, and you get Q1. Let's write this out. Is equal to 0.25 times 110 plus 10. And you can pop that in your calculator. That is what? 0.25 times 110 plus 10. And I get 37.5. So let's write that out. Maybe up here. And there's our answer. So the first quartile is 37.5, and that looks about right. it doesn't look right, you should worry. You know it's not going to be like 150 or something, or 3. It's got to be in the rectangle and closer to 10 than 120. Any questions at all on this idea of a uniform distribution? Okay, let me erase this, and we're going to get to the final question of the day. All right, so here's the question. Suppose that the number of ounces of water people drink from a drinking fountain is uniformly distributed between 1 and 8 ounces, and that the number of ounces of water that students use to fill their bottles, like this guy, is also uniformly distributed between 4 and 16 ounces. You watch Thorne take a 2.5 ounce drink out of the drink fountain, and Preston fills his water bottle with 5 ounces of water before he runs off to class. Whose water usage is more unusually small compared to the rest of the people who use a fountain for corresponding water usage? So let me ask you, what does this sound like in terms of strategy? What do you think the strategy is going to be for this question? And the hint is, we've seen it, something like it, in a different chapter. Any thoughts? While you're thinking, maybe I'll even underline a keyword. And that's that unusually. So how did we find out how unusual something was?
Z-score.
What's that? Do you remember? You might have said it, but I couldn't hear. Savannah? You can't really hear. Yeah, z-score. Okay, so we're going to find the z-score. To do that, we need the mean and we need the standard deviation, right? So the good news is that there's a formula, and you don't know it yet, but you're about to, because I'm about to write it down. So I want to go to brush. So what we can say, and this is just from the formula, is that the mean, remember to use the letter mu for the mean, is equal to a plus b over 2. And the standard deviation, by the way, the mean, that you could probably figure out yourself because it's symmetrical. So the mean is just the average of the left and the right. That's all that is. The standard deviation, I promise you, you won't figure out yourself. That is equal to the square root of b minus a squared over 12. So this is one of those, you just need to trust me. Okay, I'm not even going to pretend like I can explain why it's true, but do you trust me that it's true? Hopefully you do. Okay, so once we have these formulas, now we can just figure out what we've got. So let's start out one person at a time. So let's see who was first on this one. Thorn. So for Thorn, you watch Thorn take a 2.5 ounce of drink out of the drinking fountain. So that is X. Now, Thorn took a drink right out of the drinking fountain. That has a 1 to 8. So A equals 1, B equals 8. Any questions on that so far? Let me also remind you the z-score formula, because that's important. And that is that z is equal to x minus, I'm going to write mu because it's easier to type, divided by, and I'm going to write sigma because it's easier to type. And that's the z-score formula. So now we just can type in or figure out what the Thorn z is. So z is equal to, so now I guess before z, let's find out mu is equal to 1 plus 8 over 2. Which is equal to 4.5. Any questions so far? Sigma is messier. That one I think I'm going to have to do by brush. That's a square root of 8 minus 1. Squared over 12. Notice the 12 is inside the square root. So the square root of 8 minus 1 squared over 12, you can pop that in your calculator. I'm going to do that as we talk. So that's going to be 2.02. It's good enough. I'm going to go 2 decimals. Any questions on finding sigma? Okay. So now what we do is we find our z-score for Thorn, or his z-score. So z is equal to, now we're just going to take x, which is 2.5, minus mu, which was 4.5, okay, and then we're going to divide by 2.02. And again, that's definitely something you want to do in your calculator. It's around -1, but let me put it exactly. So 2.5 minus 4.5 over 2.02. Yeah, -1. Negative 0.99, call it -1. Any questions about Thorn's z-score? Okay, we're almost done. Now let's find Preston's z-score. So let's do Preston. I'm going to do Preston in, how about blue? So Preston had an x of 5. Now, Preston used a water bottle, and the water bottle is uniformly distributed between 4 and 16. So A equals 4, and B equals 16. Then we can say mu is equal to 16 minus 4 over 2, which is 6. And then sigma, that one I'll draw. Is equal to the square root of b minus a, which is 16 minus 4, squared all over 12. Any questions so far? Okay, oh, you know, I forgot to put the equal, so let's put the equal 6 right there. And that one is equal to, it's going to be 3 point something, but let's see. 3.46. All right, last thing to do is find the z-score. So z is equal to, so I'm going to go x, which is 5, minus mu, which was 6, over 3.46, because that's sigma. And that is, let's figure it out, about negative 0.29. Any questions? All right, let's see if you guys can all answer the question. Whose water usage was more unusually small compared to the rest of the people? What do you think? Yeah, let's take a look. Thorne's z-score is -1, and Preston's is negative 0.29. Thorne, yeah, Thorne definitely has a higher, or a z-score that is farther from 0, right? Higher negative z-score. So we can say that Thorne had a more unusually small drink. Any questions on that? All right, the very last thing I need to do is give you the secret word. Let's make it a little bigger. And the secret word is close. Because remember, when you're talking about the expected value, you say that if you do many trials, then it's likely that the average will be close to the expected value. So I always like to give you a word that is important for the day. So what I'm going to do is I'm going to unshare my desktop. And as you're all used to, I will be happy to answer any questions. And I want to remind you, you should be well on your way in doing the project now. And if you still don't have a project question, make sure you look at the Project One discussion board and see what other people have tried and what kind of adjustments needed to happen and that'll help you figure out the project. Don't use their example, but you'll see the mistakes that happened and how to fix them. So as always, I'll be happy to hang out as long as you need me to. And I have the most amazing commute, I'm sure, of any of you to get home. Anyone want to challenge me on a great commute to get home? But here's my vehicle right here. Yeah, it's even snowing right now. Very light though. Kind of light, wet snow. But I'll be happy to answer questions. If anyone has any questions.
I don't know if you still have the last problem up that you just did.
Let me share it just a minute. 1 second. Yep, here it is.
So I was still a little confused on how you got for Preston the 4.
The 4?
Yeah.
Let me find it. So it says, let me get it underlined. There it is. Right here. Because the drink count is uniformly distributed between 4 and 16 for the bottles.
Oh, okay. I didn't see that.
Yeah, there's a lot of words there, and it's usually this one. But it's not a trick question or anything. It's just sitting there.
Got it. Okay, thank you.
Okay, thanks. And I'll be happy to answer more questions. If anyone has any. Yeah, and I'll be happy to answer questions about the project or anything else too. This is a good time. Because our next webinar will be Monday, I believe, if I remember right. But I'll also be checking the Q&A forum. I'll be checking the Project One discussion forum for any questions you have there too. Okay, so good night, Pooja. Any other questions? About the tutoring. So first, Jeremiah, are you local or not? You're local, right? If I remember right? Yeah, so you actually have 2 choices. One is you can go to our library and they have tutoring, not every hour, but a bunch of hours. And there's some tutors. But again, there's an online class, so you don't have to physically go anywhere. So let me show you. Let me share. Just a second. That one. And actually, there we go. So this is the course site. And if you see, there is free online tutoring right there. There's a link to it. And then you can ask a tutor. You could also come in person to our tutoring at our library. But you don't have to. It's an online class, so it's definitely not required. Okay, other questions? Okay, have a good night, Mike. Have a good night, Jeremiah. Good night, Brittany. Savannah. Jane. Any questions? If not, we'll call it a good night. Okay, so if there's no questions, we'll say goodnight. And again, chapter 4 and 5, most people do not find those the hardest part of the class, but it's still work to do. But you want to be focused right now really on getting that project, because that's harder and more important also. It's a lot of fun. So hopefully the project goes well, and I'm here to help out. So please, let me know any questions you have. And until next week, or until you post on any of the forums, have a great one.